recording. Welcome everybody to our Openscapes and Coiled community call. This is our 9th community call. We've begun recording and there's a transcript available. Openscapes is an initiative to help researchers do better science in less time together. Through our mentorship programs, we help research teams develop habits for data-intensive science that is more open, reproducible, collaborative, inclusive, and kind. All Openscapes activities are bound by our code of conduct, and this is linked in our document. And I think Julie's been pasting the link to the document in the chat. And some of the essence of this is to be respectful and value each other's ideas, styles, and viewpoints. And we can all lead by example and match our actions to our words. So land acknowledgements are one way that we can amplify the knowledge and work of Indigenous peoples. So I live and work on the traditional lands of the Kamloops to Secwepemc, and on maps, this place is known as Kamloops, British Columbia. Kamloops is within the traditional and unceded territory of the Secwepemc peoples who have called this place home since time immemorial. And there's a link there to nativeland.ca where you can learn more about the lands that you're living on.
Great, thanks so much, Steph. Welcome everybody. I'm Julie Lowndes and I co-lead the NASA Openscapes project with Erin Robinson of Metadata Game Changers. And so she and I are here with Steph today. And NASA Openscapes is a project and a community to support researchers using NASA Earth data in the cloud. And with today's conversation, we're really excited to welcome our speakers, Amy Steiker, if you want to give a wave, Lopez, Andy Barrett, who are from the National Snow and Ice Data Center and who are NASA Openscapes mentors. And they're going to be in conversation with James Bourbeau from Coiled. You want to give a wave, James. So this is going to be a conversation and demos where they're going to share about supporting researchers using NASA Earth data in the cloud and with Coiled, and experimenting with Coiled as an approach to Earth access, and with that, how to refactor workflows and serial processes and really think about what this transition looks like and feels like in the cloud. So our plan today, if you're following along in the doc, is that we will have a conversation structured around the what, so what, now what, liberating structures framework. And throughout this document, you're welcome to write any notes or reflect with what you're hearing from the speakers at any point. So there's points in the document for silent reflection as you go. So after that part of the conversation, we'll have 15 minutes of time for question and answer and discussion. So please, as you have questions, you're welcome to write them in the document and we'll be keeping an eye on that for the discussion, or you can also write in chat. We're also building a culture here where we help each other out and learn together. So this document is part of that. You're welcome to use this and help us create a rich document that is our combined knowledge from this conversation. In the spirit of shared learning, I'm just going to screen share for 1 second to show you how you can navigate a little bit in this document. We've been using headers around the timing for the conversation today, and those headers show up as a table of contents that you can turn on and off in the view show outline. So you can navigate around this document a little bit as we go. And you're welcome to please type your questions below or as you follow along with the conversation. I'm going to turn it over to our speakers. Their bios are here in the document and you can learn more about them. And now we're going to hand it off to Andy Steiker and Andy Barrett to talk about easy scalable cloud computing with Coiled.
Okay, I think I'm gonna lead off. This is Andy Barrett, and I'm just gonna share my screen. Okay, So you should now be able to see, I think you can someone just
Yes.
confirm they can see the
Yes,
slide rather than my desktop. Great. Okay. Well, welcome everybody. I'm Andy Barrett. I'm at the National Snow and Ice Data Center, which is part of Ceres, and at the University of Colorado in Boulder, Colorado. And I'm gonna kick off just to provide a motivation and introduction to the demonstration that Amy is going to take you through in a few moments. But I'd just like to acknowledge that this is a collaborative effort between Amy, Luis, and myself getting this demonstration together. So yeah, so as motivation, National Snow and Ice Data Center is a data center. It's also a group of scientists who are focused on snow, ice, and very cold water around the globe. And one of our interests is in sea ice. It's a critical component of the climate system, a critical component of the biological systems in both the Arctic and Antarctic, and important to people who live in the Arctic as a platform to hunt from and travel and such like. So, we know a lot about sea ice extent. We have a record dating back to 1979 of the amount of the Arctic Ocean that is covered by sea ice, and also the Antarctic Ocean as well, the Southern Ocean. And we can produce daily maps of sea ice concentration. You can think of concentration as the fraction of a pixel covered by ice, which I'm showing here on the left. And we can build up a time series of sea ice extent, which tells the rather depressing story of that sea ice extent is declining and has been declining. I'm showing here the plot from September, which is the timing of the sea ice minimum in the Arctic. And so we have a lot of information about this. We have less information about ice thickness. We're starting to build up our knowledge of ice thickness changes, but it's a work in progress. And one of the ways we can do that, and obviously we're using remote sensing data. It's the only way we can get a region-wide idea of what's going on in the Arctic. And we can measure the thickness or estimate the thickness of sea ice from space using satellite instruments called altimeters. And one of these instruments is the NASA ISAT-2. It's a laser altimeter. There are also radar altimeters. Cryosat-2 is the European Space Agency's radar altimeter. Both of these operate in generally the same idea, in that a electromagnetic beam of radiation is emitted to the surface, and it gets reflected from that surface, assuming there's nothing in the way to interrupt it. And then it gets returned to the satellite, and by knowing the travel time of that radiation, you can then estimate the distance between the satellite and the surface of the Earth, and then knowing some other geophysical parameters, we can get a height of whatever surface that radiation is interacted with. For sea ice, that gives us either the height of the snow that's on top of the sea ice, if we're looking at it in winter, or it gives us the height of the ice. And that's relative to our idea of an ellipsoid that describes the figure of the Earth. What we want is thickness. And in order to get that, we first need to get what we call freeboard. And hopefully you can see my mouse, but freeboard is the distance from the local sea surface to the top of either the ice or the snow. We distinguish that snow or ice freeboard. And the way we do that with altimeters is we find cracks in the ice, leads, that allow us to measure where the local sea surface is, and then we just difference those two, the measurement of the height of the ice and the height of the local sea surface, and that gives us an idea of freeboard. And then knowing something about snow depth and densities, we can use buoyancy to get at thickness, ice thickness, which is what we want here, labeled here HI. Now, if you go back and look at this figure here, ISAT-2 and all altimeters measure along tracks. They're not they don't produce an image. It's a track of, in the case of ISAT-2, photons every 70 centimeters along the track. Tracks are spaced out by 3 kilometers. So we have a set of tracks across the surface of the Earth, but what we want is some kind of gridded product that we can then compare with other geophysical parameters. And that's really the demonstration that Amy is going to take you through. It's how do we go from tracks of ISAT-2 to a gridded freeboard product. Now, ISAT-2, as I said, measures photon heights every 70 centimeters. That's a lot of data. And so we need to be doing this. It will take a long time for you to download that amount of data to your local computer, and even more time for the processing of it. So being able to do that in the cloud, and ISAT-2 data is in the cloud, presents a huge advantage. Now, we've developed this workflow as tutorials, and we developed it in using a Jupyter Hub with notebooks. But there are other ways of working, and probably all of you probably work using scripts as well as notebooks. And so I really wanted to kind of highlight that there are different ways of working. And I think what Coiled offers us is this way to, you can use scripts in a notebook, in a hub, but Coiled offers an alternative way of working with scripts that might be more familiar to how we work. So hopefully that's provided a little bit of an introduction to what Amy's going to take you through now. I'll stop sharing and hand over to you, Amy.
Great. Thank you so much, Andy. That was a really excellent introduction. So I'm going to just go ahead and share my whole desktop here, and I will now jump straight into going into a little bit more detail, picking up where Andy left off as far as that image describing a real world example of working with this ISAT-2 data. So what I have on the left-hand side of my screen is that figure, which again is demonstrating this use case. In this example, actually on the left-hand side of the screen, this is a Jupyter notebook that we did put together that lives in our NSIDC data tutorials repository. And it walks through this use case of, I'm interested in this ISAT-2 data set. This is the ATL10, it's that sea ice freeboard height. And that data set, as Andy mentioned, it's really large, but you're getting these height values along those tracks that Andy described. And so in some cases, you may want to do some further sort of manipulation or aggregation, or in this case, some regridding. Let's say you want it over a given resolution, over a given time period, and maybe, apply some projection parameters that maybe don't exist in some of those higher level gridded products. And so just watching the chat as well. Thanks, Andy. And so what this notebook is doing, and I'll kind of back up a little bit and walk through some of these learning objectives. We essentially want to grab the ISAT-2 data over our time and area of interest. In this case, we're using the Earth Access Python library that provides that functionality in a very easy way across all NASA Earth data. We want to open those files using this H5 Coro library that efficiently reads the data, which is in HDF5 format, directly from the cloud, as Andy mentioned, and then loading all that data into a GeoPandas data frame. And then we'll perform some gridding operations. So this is a very large operation and can take a lot of compute resources to do that. So what we've done is we've converted this workflow into a script. So this is this workflow.py script, and it's essentially, again, performing all of these same operations. So I'm going to go ahead and demonstrate what this looks like using just a terminal. And again, as Andy walked through, there's that use case of working just with a Python script locally on your computer from your terminal window in this example. So what's happening here, all I've done is I've cloned this repository. I'm in the directory where the script lives. And I can first just activate the environment. If you're familiar with Python, essentially just activating an environment that I've created that has all of my Python dependencies needed for that Python script. The next step is to log into Coiled. So I think James is going to walk through this in more detail. We'll kind of back up and talk through these steps in a little bit more detail. But all I've done is after I've installed Coiled, I have to log in. I get a window that's just essentially asking me to authorize my access to my Coiled account. So this is all done. I could go ahead and close this window now, head back over to my script. And then what the script is doing, so I'm just running Python workflow.py. I'm specifying my year of interest. So in this case, I want data over 2019. I have a bounding box. In this case, I've actually expanded my bounding box beyond the raw sea. I'm asking for all data over Antarctica. I'm specifying that I want to run this in the cloud, and then I'm specifying an output directory. So what's going to happen here is it's going to walk through, we're going to walk through and find the ATL10 data using the Earth Access Python library. We authenticate against Earthdata login, which is what you need to access data, all NASA Earthdata. What it's doing here is it's searching for ATL10 data over the year 2019. It found almost 12,000 files, 1,200 files. And there's actually quite a lot of data when it comes to, the points as far as like the segment location, and to get those height data, we essentially grab over almost 600,000 rows of data. So really this took about, I think, less than 20 seconds to get that data, pull it into that GeoPandas data frame. And then what this script does is it actually outputs that data frame into a GeoParquet file. And then you can go ahead and perform your gridding analyses. What's happened here, you could see a couple of other steps below where it's attaching to a Coiled cluster. It gives you information on that cluster. I think James will walk through that user interface in just a moment. And all of that analyses, all of those computations to grab the data and combine them into that single data frame is all happening in the cloud, even though I ran the script locally from my terminal window. The reason it could do that, if you look over back into the script on the left-hand side of the screen, what we've added to this Python script is something called a decorator function that is essentially telling us if we want to specify run this in the cloud, we specify this Coiled function, we tell it what AWS region to run into, the memory that we need, and kind of how long we want the cluster to stay alive for. And then it does some adaptive scaling. So there's sort of no guesswork involved here. It does all of that for you to scale to the amount of compute that's needed for that analysis, and then you get your output. Again, that's all running local. You're running the script locally, but the computation is all happening in the cloud. So it's a little bit of the show, and then I'll hand it over to James now, who can dive into a little bit more detail of kind of telling what's going on behind the scenes.
Yeah, thanks so much, Amy. That was really cool to see. Let me go ahead and, well, I guess before sharing my screen, thanks everyone for having me. So yeah, I'm gonna zoom out a little bit and talk about cloud computing and Coiled a little more broadly. Then I'm gonna focus on a couple of common use cases we've seen with folks who analyze geospatial data. And then, like Amy said, also sort of go into some of the details of what's happening under the hood in Coiled to hopefully make our lives a little easier. going to go ahead and share hopefully the right desktop and you're seeing the Coiled webpage at this point. If that's not the case, let me know. So yeah, sort of the big picture goal for Coiled is to make it easy for you to run your code in the cloud at scale. So in a straightforward manner that frankly is hopefully, like, as a Python user, kind of delightful to use. And we do that in a few different ways. As I'm sure you're all aware, Python is very dynamic and people use it in lots of different contexts. One of our sort of design principles is to meet users where they are. And because people use Python in so many different places, we have a few different APIs to like match those use cases well. Due to the time we have today, I'm just going to focus on these first two APIs. So coiled functions that Amy and Andy just showed off for running arbitrary Python functions in the cloud. I'm also going to talk about coiled clusters. So Coiled also makes it easy to spin up large DAS clusters in the cloud for your analysis. So for those, just in case you're not familiar, Dask is a popular open source library for distributed and parallel computing, and it scales the PyData ecosystem. So it scales libraries like Pandas and NumPy and Xarray and Zar, things that you're hopefully familiar with, to larger than memory and distributed use cases. I'm just going to touch on a couple of our other APIs. We also have a nice simple API for running Python scripts in the cloud. And we also have an API for running Jupyter Lab servers in the cloud as well. Not going to go into details on those today. If folks have questions, I'm happy to follow up in the Q&A later. Okay, so with that, let's dive into a couple of examples. So this first example follows a similar pattern to what Amy just showed. So it's we've seen this pattern over and over again with many groups working with NASA data. The pattern is basically, I have a bunch of data files on the cloud that I would like to process. I have like a Python processing function that processes one of the files. And I just want to take that function and map it across all of the files in the cloud. Please run that for me, at scale. So this example here, again, kudos, shout out to Earth Access. If you're working with NASA Earth data and you're in Python, Earth Access is probably the library you want to be using to access that data. So here we use Earth Access to search for a particular data set, and I'm looking at a particular time slice here. Oh, I should have mentioned this earlier. Someone let me know if the screen's not big enough, if I need to enhance further. So yeah, so here I have this data set. I have, roughly 1,400 data granules. And then here I define my processing function that I want to apply to all these data granules. Actually, I'm just going to comment out the coiled stuff for a second. So here's our function. It takes in a granule, and this code hopefully looks familiar to folks. We get all the data files that are associated with that data granule. We use fsspec and Xarray to open up those files. In this case, it's just a bunch of netcdf files. And then we do some data selection. So we slice to get a particular, longitude and latitude area we're interested in. And we do some other data quality selections as well. We then concatenate all the results together and return that result. So this function should hopefully look familiar or similar to something that you're doing in your everyday research process. So right now, if I run this function, it'll run here locally on my laptop. That's where this Jupyter session's running. If I wanted to run it in the cloud, like Amy mentioned before, I'll just add this coiled function decorator. That then tells Coiled, hey, take this function, please spin up a VM on the cloud. There's some other specifications for that as well. Like the region, I want this VM to be spun up in the same region as my data. In this case, it's US West 2. Please run that function there on a VM and return the result back to me in my laptop. So yeah, let's go ahead and define that function. And now let's run it and talk a little bit about what's happening under the hood. So here's my function. I'm going to run it just, in this case, on the first data granule. I'm going to get that processed result, and then I'm going to plot it to get some result out. So what's happening here is Coiled is scanning my local environment. It's looking for all the Conda installed packages I have, all the pip installed packages I have. If you have any editable installs, like if you've ever done, pip install -e for some package, it's finding all of that. It's bundling that all together for us and shipping it off to a VM that is being spun up in the cloud for us. This is actually one of the sort of first hurdles people run into when transitioning to running their code in the cloud. How do I get all the packages I want installed, that I have locally installed on the cloud VMs? So Coiled is kind of handling all that for us under the hood here transparently. I'll go ahead and click this link here to go over to the Coiled app, and we can see sort of the progress of this VM. So here's sort of a time series of the state of this VM. You can see it was queued for a bit, that's the yellow, then it was starting up, then now the instance is running, and then over here, when we're in this darker blue, it's now downloading all that software environment that I have locally installed. It's now downloading that all onto the remote machine. It's in US West 2, like I selected. I didn't specify a specific instance type. Amy, in her example, said, I need this much memory, and Coiled chose the instance type accordingly. Here, it's just using our default instance. And our instance is actually up now, and it's running, the processing function. That whole process takes typically about 1 minute or 2 minutes to spin up and download all of the software onto the machine. That's about as fast as you can spin up a VM on AWS today. And switching back to the notebook, here's the result. So that whole thing, spinning up, provisioning the machine, downloading my software, actually running the function, returning the result, took about 1 minute and 40 seconds. And here's the plot. It's a little choppy because, again, this is just the first data file. Let's now go ahead, instead of not running on one file, but actually running it on all of the files in this data set. So I'll do that here. So Coiled functions, what you might do is do a for loop, just say, for all of my file and all of my files, run my processing function. You could totally do that, and that works well. Coiled functions, however, have a map method, which is very similar to Python's built-in map function. And what that allows you to do is take your function and actually apply it across a whole list of inputs, in this case, all the granules in our data set. And it doesn't only just run the function across all the granules, it actually does that in parallel. So what we'll see is, if I go over here, Coiled is now adaptively scaling up. The amount it scales up depends on the load that you give it. If I give it 10 files versus 10,000 files, it'll spin up a different number of VMs to accommodate, such that the whole workload finishes in something around 5 minutes, a handful of minutes. We can see in this case, I've spun up 8 instances now. So I've jumped from 1 VM to 8 VMs. So if I go to the dashboard here, we can see that first VM that I spun up is sitting here and just kind of churning through files. Here are those almost 1,400 granules in this data set that we're just kind of chugging through. And in a few seconds, we'll see other machines that were being spun up arrive, and then we'll start churning through. And yeah, here we go. So now I have 1 VM, 2 VMs have showed up. Eventually we'll get up to, I think, 8 VMs. That is spun up. And now we're just churning through the same exact data set, but now we're churning at a much faster clip. So we're going to have a more sort of interactive process here. Yeah, so this is going to churn through this data. It'll return the result back locally to the laptop, and we'll get our plot, but now on the full data set. I'll circle back to that in a second. This is just going to run. It'll take about a minute or so, but just for the sake of time, I move on to the second example. So this example showed running just arbitrary Python code. Here's a Python function. I want to run that in the cloud. Another common use case we see is people using Coiled clusters, so Coiled DAS clusters and Xarray together to do a large geospatial analysis. In this notebook, we're going to be looking at the National Water Model data set that's it's publicly available on AWS's Open Data Registry. So this data set is quite large. We're going to be looking at just 1 year of this data set. So we're going to look at the year 2020. It has a pretty fine spatial and time resolution. Spatial resolution is 250 meters. The time resolution is every 3 hours. So just at that resolution for this 1 year, the whole data set's about 6 terabytes large, which is definitely much larger than I would want to run on my MacBook Pro. So for the sake of time, I've actually run a few of the cells all the way up to the big computation ahead of time, actually while Amy was talking. And we can see here I'm spinning up a coiled cluster. I also want to highlight, this is the only coiled specific code in this example. All the other cells are just standard normal looking X-array, NumPy, and matplotlib code that you're probably familiar with. So here I'm telling Coiled to spin up a DAS cluster for me. Spin it up in US East 1. That happens to be where this data set's stored. I'm asking for 50 workers. So this is actually going to spin up 51 actually different VMs for us and of a specific type. Here I've requested, before I didn't request a specific instance type, here I am. You can, any VM type that's available in AWS, you can choose here. And that spun up. Again, we get all this sort of niceties that we get with coiled functions. We get this automatic package syncing for us. We get nice visualization and monitoring of it. And that whole process took about 1 minute and 11 seconds to spin up that entire cluster in the cloud. We then use X-array to open up this large national water model. It's just a big ZAR data set in AWS. It has a lot of different data variables. We're interested in this one, which is the water table depth. So we can see this full data set is 250 terabytes. So by many standards, that's a big data set. Certainly more than I'd want to analyze on my laptop. For just sort of timing purposes, I'm going to select a single year, 2020. That's still reasonably large. It's 6 terabytes large. I'm then going to open up a TIFF file that has information about counties across the US. I'm going to join that with the National Water Model data set. And then I'm going to do a group by of that. I'm going to take the data set, I'm going to group by all of the individual counties in the US. I'm then going to compute the mean of this variable to get the average water table depth. So that result itself is pretty small, fits in memory, 70 megabytes, but actually computing that requires a large computation that scans over that 6 terabyte data set, which I do here. So that just launched a computation on this cluster in the background. I'm going to go ahead and pull up for those who are familiar with DAST, you'll know it has a bunch of really nice diagnostic tools to get a sense for what's going on in the cluster. So here we can see, here's the actual computation happening on the cluster. We can see the task stream on all the individual workers. We can see all the tasks that are part of this computation happening. I can then see, for example, progress for the different types of tasks. Here, X-array is opening up the data set, selecting a column, doing some rechunking, I'm doing some group bys, I'm computing means of those individual groups and sort of aggregating those results together. I can also see the memory load on each worker in the cluster. So of those here, there's going to be my 50 workers. I can see how much memory is being used across them. And we're just going to kind of churn through this 6 terabyte data set, and it will finish in a couple of seconds. Once I get that result, I can then kind of massage it a little bit, as we're all familiar, to get it into a form that I can actually plot the actual sort of data set I want. That happens here. And then I can plot the results with matplotlib. And that's just sort of standard matplotlib code. And our computation is almost done. And there we go. And here's the plot. And we can see, so now we can see the average water table depth in meters just across the US that we just churned through 6 terabytes, excuse me, of data, and it cost about $1. I go back to the other notebook. Here's that plot across the entire data set. It took about 4.5 minutes to do. So with that, I'll say thanks all again for having me. I'll turn it over to Luis.
Can you hear me?
Yes.
Cool. Yeah. So I don't have fancy demos to show. I'm Luis Lopez. I work at NSIDC as a software engineer, and but I guess I'm kind of giving the overview of these approaches. I think they're very valuable. As Andy mentioned, there are many ways of working with data. There is not like a single path for doing things. And I'm glad that there are companies like Coiled that build on top of open source software and contribute back to the community and produce, and not just Coiled, but there are other companies that are doing this approach for markets that are not necessarily, the most profitable, because they could be working, just focused on other stuff like finance only. And one of the things that I really like about working with all these different companies like 2I2C and Coil and is they're trying to lower the barriers for the scientists. At the end, I think it's all about like how can we facilitate the workflow for them so they can start working on the science faster. As a technology, I think the good thing about Coil is it doesn't get in the way of your workflow. Like James mentioned, the only Coil specific thing would be an annotation in the function or provisioning the cluster. The rest, it's open source software. I think it has its place in the community. I find it very useful for certain workflows and also for people that might not have the privilege of working with or working with like if you don't have access to these kind of resources through our institution, it'll be difficult to by yourself sometimes try to do all this stuff because you'll have to get into the cloud and eventually it will probably be simpler to just like do it in your laptop, and a lot of people I've seen it like just mentioning like, oh, it's going to be in the cloud is a barrier. So I think it's a great technology. We at NSIDC are exploring different ways of working with the data that we have. And another important thing is to mention that half of the magic would be the provisioning of these resources, and the other half of the magic would be some of the libraries or the libraries that we're using it. For example, in the example that Andy and we did for the freeboard, we're using H5 Coro, which is a very performant way of reading HDF, make things faster. In the example that James did, there is also another library that does the grouping in X-ray way faster. I think Deepak is here, the one that developed it. So there are like a lot of contributions to make this, things in a more approachable way. And I think it's important that for scientists, you have more options to work with stuff. And I think that's kind of like my 2 cents on why we opted for using this as another avenue for them.
Great. Well, thank you to all of the speakers. And as we transition into the discussion piece, and I see there's a lot of questions both in the chat and in the document. I was just curious if any of the speakers had any questions for each other or follow up as we get into the discussion.
I just want to kind of quickly +1 Luis's point. I didn't mention this before. My background is in astroparticle physics, so not like NASA geospatial things, but same ballpark. So I'm aware of what it's like to be a researcher doing science. And yeah, like one of the big problems I encountered in grad school was like people are obviously very capable and knowledgeable like in their domain, whether it's climatology or whatever the case may be. But they're not necessarily like cloud computing experts. And that's not also really the goal. It kind of gets in the way, sort of like we said, of actually doing the thing they care about, which is the scientific research. So anyways, I personally am biased, but also passionate about Coiled because I think it really does lower that barrier to entry. It helps you kind of not need to worry about those barriers for cloud computing, and helps you really just kind of focus. It's very similar to the local experience that you're hopefully familiar with. So anyways, just wanted to kind of +1 what we said.
Great. So I'm looking, there's been questions that have and conversations in the doc. Puneet, your first question about formats and data structures and evolution going forward. I didn't know if you wanted to voice anything there, or whether your question was taken care of.
Yeah, I mean, I don't really have anything specific to add on that right now. It sounds like, there's, it sounds as though there's sort of a, well, I don't know. I guess I'll just leave it there for now because I feel like he mostly addressed it there. We can talk offline.
Just for people following along, that question was at the bottom of page 6. I also wonder, Matt, if there's anything, Matt Rockland, you want to highlight from the questions that you've been answering.
I thought Puneet's question was really good, and maybe people aren't actually tracking the text conversation. I'd encourage, if you're comfortable, like sharing it. Like I gave my response, but not necessarily the best response. Like James might have thoughts, other people in the room might have thoughts. It's good, I think, seed for conversation, even if I've already given an answer. If you're game, no pressure. Maybe I'll ask a variant of the question to James. James, this coil stuff seems amazing. I'm like just really excited to pay money for this. But I'm like nervous about like tying myself into technologies. Like how does Coiled, like the space that cares both about moving fast, because we need to sort of adapt to these sort of massively changing changes in scale and technology. Those are a space that cares a lot about like longevity and like file formats that will exist for decades. Like how does Coiled like fit into that landscape? Should I be concerned? Should I not be concerned? How to address that nervousness if you can?
Sure. Yeah, I think the short answer is no. You shouldn't be concerned. In the example I showed with the Earth axis, we're analyzing a bunch of NetCDF files. Like the coiled function was just a tiny bit there that you can remove, the little decorator. We are really just running your code in the cloud. So if your code handles geotiffs or a more modern, like a ZAR data set, or if you're working with stack data, Coiled really just runs that code for you on the cloud. So as long as your code is sort of compatible and working with those formats, Coiled doesn't really get involved. Coiled doesn't really have an opinion on that. We run your code for you in the cloud. So it's a pretty, if like lock-in is the concern, there's very minimal lock-in. It's just Coiled is kind of icing on the Python cake that gets you on the cloud. Hopefully that answers the question.
Great, thanks. I see some folks have turned on their cameras. We could also have folks raise your hand and voice questions out loud along with the doc. And as you think about that, there's been questions about cost that have been answered by Matt in the chat and in the doc. And cost is always a question about how much the cloud processing will cost. So the Coiled dashboard lets you see those costs, and Matt has responded as well that that process we saw James run was probably about 10 cents.
I might give a
James,
quick visual.
Can you show the dashboard?
Yeah, I was gonna say I might give a quick visual answer as well to that, just because this comes up often. So here I'm running in a particular Coiled account. I can see that function and that cluster I spun up earlier. This is nice because you get how long things have been up. You get approximate cloud costs, like the rate. That function cost me 10 cents an hour to have a VM up, and tells me how much I've used so far. So anyways, we get a really good sense of cost. I can see historical usage too. Like all of my colleagues here, Hendrik was running some stuff earlier. He spent 50 cents. I was running something earlier that was a little more beefy and cost $10, for example. You can also, so that's like one side of the coin, is you get visibility into how much you're spending. The other side of the coin is you can set maybe this is the more important side. You can set limits on spending too, which is important. So for example, I can go to the team page here. I can see all my colleagues. I can set core and credit limits either for individual users or for the entire team. So if I, have a 10,000 core limit, the second I try to spin up a 1,000 core limit, if I then try to spin up my 1,001st core, I get a nice informative error from Coiled saying you've exceeded your limit. Same for the credit spending too. So anyways, that's just another visual answer there. So.
And James, one other thing before you stop sharing that, I think one other thing that I like as an administrator of a Coiled team is the ability to switch billing. And so I think, as I understand it, that a user could be on a Coiled team and then could be switched to another Coiled team and they could change the credit card. So like if they're moving from our project to their own grant, that switch on the backside is pretty easy.
Absolutely. Yeah, it's very easy to set up your own workspace. Maybe you have maybe you're part of multiple teams and they each have their own unique billing situation. So like I'll just briefly, because Matt's on the call, I'll briefly just change his limit really quick. It's really easy. I can change his core limit to, I don't know, 11,000 or something. And now Matt just got 1,000 more cores he can spin up. Go have fun with that. So yeah, that's sort of the interface there.
Awesome. Thanks, James. Rob, I see your hand up.
Yeah, thanks. This has been a very good practical presentation. I was wondering if one of the Coiled representatives could speak to a couple of different compute hosting scenarios. One I can picture that's very straightforward is for the hosting institution, the one that's the repository that's actually holding the data, to offer a space on their one of their accounts that would host those EC2 instances driven by Coiled, and then the cost can be worked out there. There's also another case of where you can have customers set up their own cluster in the same availability zone, resulting in low download costs. That in that second scenario, can you also have the customer run Coiled compute on their own system and accessing what is effectively a remote data repository, but has modes of exposing their data sets?
So I think I'm going to answer, and then Matt, feel free to reply to my answer. For the first one, so Coiled actually runs inside of your AWS account. The design there is, you give us sufficient credentials in your AWS account, we will handle the provisioning and, pulling Docker images and tearing down of resources. So Coiled always acts inside of your AWS account or GCP or whatever cloud provider you happen to be on. This is also nice for like, if you're working with private or sensitive data, we don't ever see it. It's all inside your account. For the second one, I might be misunderstanding your question, but I'll just say, you can run Coiled from anywhere you run Python. So for example, I ran Coiled here in my Jupyter Lab session on my laptop. We've also seen Coiled run, on scripts in Jupyter hubs that, Openscapes is helping maintain. So that's like in a different AWS account somewhere else in a Jupyter hub, you are running Coiled there.
Let me jump in.
So you can run from GitHub Actions as well. Yeah, maybe I'm misunderstanding.
What I heard from Rob, and correct me if I'm incorrect, Rob, is that like you might be someone who has a bunch of data and you want to increase access to that data. Much like Noah posted the data that James was playing with the National Water Model, or whoever was hosting the data with the CI stuff. But James was able to access that data from not Noah's Amazon account, but from his own Amazon account. Yes. And so what worked there, what's very common with public data, is to use a requester pays S3 buckets. So you host your data on Amazon S3, but you don't want to like foot the bill, because people start downloading that data, the egress charges can get quite intense. And so what you do is you do requester pays. You mark the bucket saying, hey, look, this is public, anyone can get it, but the charges go to whoever downloads that data, they don't go to me. And then it's free to download the data as long as you're inside of that same account. And so Noah can host data on Amazon, they mark it as requester pays. And when James goes to run his demo, he just makes sure he's in the same region. He can access that same data on Amazon. If you make an S3 bucket public on Amazon, it is public to the world, so anyone can read it from any account. Is that helping? Is that the direction of your question?
Yeah, it's getting in the right direction. Now let's take egress costs out of the question for a second. Let's just say the data repository, vast data sets, they don't want to actually implement coiled services, but the researcher thinks it's really cool and they want to do that. So what if they set up their own cluster, their own AWS cluster, and they point Coiled to running to that? They authenticate Coiled and running that. This means that the researcher has full control in terms of their cost structure and what they're using for resources. Is that a viable scenario for a data repository to point people to and to say, hey, consider using this on your cluster? We'll open the doors as much as we can. Maybe we'll have open data that has no egress costs. That kind, those strategies are viable.
Yeah, I think that's actually exactly what we're seeing here, right? We didn't collaborate with NOAA to access this data. We didn't collaborate with NASA to access this data. They've just made it publicly available. None of those organizations know what Coiled is, right? Coiled is too small to like even a blip on their radar. But because Coiled just works very natively with cloud resources, there's not like a special Coiled cluster. Coiled is just turning on and turning off VMs. It's very native cloud technology. It's very vanilla. It's very boring from a sort of a cloud security IT perspective. And so it's very easy to integrate. It's very easy to use from anybody. If anyone here has an Amazon account, they can spend like a minute, give Coiled access to their Amazon account. And then Coiled just turns on and off VMs for you. It is as though you just had a very smart cloud admin next to you.
And the researchers don't have to figure out how to do this stuff. They don't have to figure out how to set up these resources and stuff. So it's very enabling.
Yeah.
The onboarding experience.
That's why we like it.
The onboarding experience, we've worked pretty hard to make sure that, like, I don't have any cloud experience, to be frank, and like I can use the product. If you can like understand how the terminal works, you type in Coiled setup AWS and hit enter a bunch of times, it'll set up everything for you in a way that doesn't cost anything. So it's very much designed around the sort of target user of someone who's very sharp in their science and their discipline, but does not have a whole lot of cloud experience. I think the people on this call this is sort of the cloud product that is designed for you, which is different from some other cloud products. It's actually kind of hard to get like how Amazon Lambda works. It's like you have to go and like get a small master's degree in Amazon certifications. So hopefully that answers. Great.
Cool. I want to try to get to Tyler's question quickly. Tyler, we might need to take it offline, but I want you to at least have the chance to ask it.
Sure. I guess I'm mostly curious about the debugging process. It's great to see demos, but most of the time it's not usually getting started that takes so long. It's the iteration of like figuring out what went wrong with your code, especially if you're pulling thousands or tens of thousands of files. The data provider might have screwed something up in one of the files. So I'm curious, like, what is the process for debugging? Can you actually figure out what got sent to a particular worker and then debug it locally? Or how do you go about getting it to work on every single file?
Yeah, so great question. As you can imagine, there's a couple different ways debugging is like a fun art. So yeah, Coiled makes it like all the errors you get high visibility into them. You can see them all on the dashboard for your function in your cluster. So you can see exactly what went wrong. You get the full trace back. So yes, that's like, oftentimes that's the useful information. Another thing we often see is people actually start out not running on the cloud, but start running locally. So both Coiled functions, instead of using Coiled clusters, you can use like a local DAS cluster. And they might run locally on, instead of 10,000 files, one file or two files or something like that, to really iron out the details and make sure they're getting the result they want on there. And then once they're sort of confident in that, then they'll switch from local mode and then switch from local mode rather to running on the cloud, on the full large problem. Hopefully that's getting at your question a little bit. But the debugging tools here actually aren't really Coiled specific. They're all the normal debugging tools you would use when running any kind of DAS code, or for Coiled functions, any kind of just Python function. So hopefully that's helpful.
Thanks, James. And I think that's a nice segue. I'm going to take a little bit of facilitator license, and instead of covering a lot of our closing, I one more question from Jessica about how do I know if my code is Coiled compatible? And James, I just want you to have an opportunity maybe to tell people how they might connect with us and how they might know that too.
Yeah, for sure. So again, we just kind of run your code in the cloud. Oftentimes that code can be inefficient. We've actually been working with lots of groups at NASA through Openscapes, or in collaboration with Openscapes, I should say, to sort of help that cloud optimization process. So anyways, if you are interested in getting in touch with us at all, you can follow up with me directly. My email's, well, james@coiled.io. Hopefully that's easy to remember. Or you can follow up with any of the Openscape folks. You can follow up with Julie or follow up with Aaron. We'd be happy to get in touch.
Awesome. And so with that, we are at the top of the hour almost, and we're at the bottom of page 8 if you're following along. I really appreciate everybody who showed up today, to our presenters, both from Coiled and from NSIDC. That was awesome. And this was a really interesting group of people coming together to learn about our experience using Coiled so far. There are links to get in touch with us, and we will have a blog post and a recording of this posted on the Openscapes website in about a week. And we would love to hear how you're using Coiled if you end up picking this up. So I guess we will leave it there. Thanks so much and have a good rest of the day.
Thanks, everyone.
Thanks, everyone.
Yes.